Welcome to Dark Cosmos Theory. Before we dive into today's exploration, take a moment to hit that like button, subscribe to the channel, and drop a comment letting us know where you're watching from. Your support helps us continue bringing these cosmic journeys to your screen. The transformation happened faster than anyone anticipated. Just a couple years back, whenever astronomers discussed the earliest epochs of cosmic history, every statement required careful qualification. Our vision into deep time remained clouded by uncertainty. The stellar nurseries of the primordial universe existed only as theoretical constructs in our models. The architecture of infant galaxies lived primarily in our imaginations, and regarding worlds orbiting distant suns, we operated almost entirely on conjecture, piecing together fragmentary clues and constructing hopeful scenarios from the thinnest evidence. We stood at an observational threshold, perpetually aware that our instruments couldn't quite reach far enough, couldn't quite see clearly enough, couldn't quite resolve the details that would transform speculation into certainty. Every image from the deepest surveys represented an act of faith as much as science. Every model of the early universe carried the implicit caveat that we were extrapolating far beyond what we could actually measure. The cosmos beyond a certain distance remained fundamentally mysterious, accessible only through mathematical inference and theoretical projection. Then came the awakening of James Webb. Within weeks of achieving operational status, the fog of uncertainty began to lift in ways nobody had quite predicted. The detection of alien worlds evolved into something far more profound than mere identification. We started identifying the actual chemical compositions breathing through their atmospheres, molecule by molecule, compound by compound. Those fuzzy pinpoints representing galaxies from cosmic dawn transformed into detailed portraits of fully developed stellar cities that violated every timeline we'd carefully constructed over decades of painstaking research. These revelations emerged not gradually, as scientists had expected, but explosively, within mere months of the telescope achieving operational status. The disruption hasn't stopped. James Webb continues methodically dismantling our comfortable assumptions, one observation at a time, one target after another, building a new picture of cosmic reality that looks nothing like what we expected. It reveals phantom galaxies that mysteriously ceased their stellar production eons before any known physical process should have silenced them. It detects molecular combinations drifting through exoplanet skies that challenge our understanding of atmospheric chemistry and planetary evolution. Anyone hoping this instrument would simply validate existing cosmological models clearly hasn't been paying attention to the steady stream of papers emerging from the astronomical community. This telescope arrived to upend, not to confirm. What follows isn't a retrospective on the engineering marvel itself, though the telescope represents one of humanity's most ambitious technological achievements. Nor is this a meditation on the decades of anticipation that preceded its launch, though that story carries its own fascination. Instead, we're examining the actual scientific harvest, the chronological sequence of observations, the concrete findings that emerged with each pointing of those 18 hexagonal golden mirrors toward another patch of cosmic darkness. The genuine narrative of Webb doesn't reside in its technical specifications, impressive as they are. It lives in the discoveries themselves, in the data that keeps flowing back to Earth, in the observations that keep forcing us to reconsider what we thought we knew, and several of them continue to defy coherent explanation even as more data accumulates. When that inaugural deep-field photograph arrived on July 11th, 2022, the immediate response from the public was pure aesthetic appreciation. It resembled an impossibly detailed cosmic tapestry, a minuscule fragment of sky amplified to reveal its hidden complexity in ways that seemed almost unreal. The image quality surpassed anything humanity had captured before, but after the initial visual impact faded, After people moved beyond simply saying how beautiful it looked and sharing it across social media, the scientific community began extracting meaning from the details. That's when the real implications crystallized, when the true significance began to emerge from careful analysis. That solitary photograph contained thousands of galaxies, not individual stars scattered through our local neighborhood, though those appeared as well in the foreground. Not planets dotting our solar system's terrain, though Webb would turn its attention to those soon enough. Entire galaxies, each one harboring billions of stellar furnaces, all compressed into a patch of sky you could cover with a sand grain held at arm's length if you were standing on Earth's surface looking up into the night sky. The official designation was SMACS 0723, a colossal galaxy cluster residing approximately 4.6 billion light-years away in the constellation Volans, a faint southern constellation most people have never heard of. The technical nomenclature mattered little compared to what the image revealed about the universe's structure and depth. This marked humanity's first truly clear infrared window into the universe's architectural depths. Previous telescopes had glimpsed this territory, but never with such clarity, never with such resolving power. And the view extended far beyond simply cataloguing distant stellar cities scattered across space. The image captured bent luminosity, arc-shaped distortions, spectral forms stretched and warped across the fabric of space-time itself in ways that revealed the underlying geometry of the cosmos. These distortions weren't photographic artifacts or instrumental errors that needed correction. They represented gravity's fingerprint written across the universe. Massive foreground clusters were deflecting the light from even more remote galaxies positioned behind them, creating a natural magnification effect that astronomers call gravitational lensing, a phenomenon Einstein predicted over a century ago, but which we can now observe in unprecedented detail. That warping wasn't merely aesthetically striking, though it certainly was beautiful in its own right. It served as an observational tool of immense value, essentially giving us free access to magnification we couldn't achieve through engineering alone. Gravitational lensing functions like a telescope constructed from pure space-time curvature, from the bending of light itself. It amplifies, it exposes, it grants access to phenomena that would otherwise remain forever beyond our observational reach, too faint and too distant for even our most sophisticated instruments to detect directly. Through this natural magnification provided by intervening mass, that first deep field image already contained galaxies whose light departed more than 13 billion years ago, originating just several 100 million years after the universe's violent beginning in the Big Bang. That temporal reach alone represented a stunning achievement, pushing our observational boundary back to epochs we'd only theorized about previously. But the aspect that truly caught the astronomical community unprepared wasn't merely the age of these galaxies or the fact that we could see them at all. It was their appearance, their characteristics, their level of structural development. Several of them exhibited excessive brightness relative to expectations, well-defined structural organization that shouldn't have been possible yet, and advanced evolutionary stages that contradicted fundamental predictions built into our best models of cosmic evolution. According to the prevailing models governing early cosmic evolution, galaxies from that era should have appeared small, chaotic, and still assembling their first generation of stars. Primitive, essentially, like teenagers still figuring out their identity. These should have been galaxies in the process of becoming, not galaxies that already were. The theory suggested they'd be irregular blobs of gas and dust with pockets of star formation scattered haphazardly throughout, systems still working out the organizational principles that would eventually transform them into the majestic spiral and elliptical galaxies we see in the modern universe. Yet Webb's first deep field revealed something dramatically different from these expectations. smooth structural formations that implied millions of years of gravitational settling, clearly delineated stellar concentrations that suggested organized star formation rather than chaotic initial bursts. Evidence of star formation processes that conventional physics suggested should require hundreds of millions of years to develop fully, timescales that would need generations of stars to live and die, dispersing heavy elements and gradually building up the chemical complexity we associate with mature galaxies. Time the universe simply hadn't provided at that early epoch according to our chronology. Immediately, questions began accumulating faster than answers could be formulated. Were these galaxies manufacturing stars through some accelerated process we'd never witnessed or theorized about? Were they assembling through mechanisms that bypassed the gradual stages our models predicted as necessary? Or had we fundamentally miscalculated the entire chronology of the early universe, getting the timeline wrong by enough to completely alter our understanding? Each possibility carried profound implications that would require rethinking major aspects of cosmology. This happened on day one of Webb's scientific operations, before the telescope's instruments achieved complete calibration, before engineers had verified performance across all operational modes, before the full suite of capabilities had been thoroughly tested across diverse targets and observing conditions. It had already forced cosmologists back to their theoretical drawing boards, back to re-examining assumptions they'd held for decades, not because the data arrived unclear or ambiguous, leaving room for multiple interpretations, but precisely because it came through with crystal clarity, sharp and undeniable. It refused to confirm expectations. Instead, it challenged them directly, immediately, unambiguously. The remarkable aspect is that this wasn't some prolonged survey requiring months of painstaking observation, carefully accumulating photons night after night. It was essentially a snapshot captured in less than a day of total exposure time. A brief glimpse proving that even in the apparent emptiness between more obvious cosmic landmarks, even in regions of sky that appeared blank to previous generations of telescopes, entire universes lay concealed in darkness, silent and invisible until the appropriate lens finally arrived with sufficient sensitivity to coax their ancient light into visibility. That lens was James Webb, and in mere hours of observation, it fundamentally redrew our cartography of the early cosmos, forcing us to acknowledge that the infant universe was far busier, far more complex than our theories had suggested. An observatory like Webb wasn't designed exclusively to probe the ancient past, to peer back toward cosmic dawn and the first moments after creation. Its engineering specifications included the capability to examine much closer targets, objects within our own cosmic neighborhood that previous telescopes had studied but never quite seen clearly enough. Not galaxies separated by billions of light years requiring us to look back through cosmic time, but stellar systems practically next door in astronomical terms, systems we could observe as they exist now rather than as they were billions of years ago. Worlds orbiting their parent stars, worlds humanity has pursued for decades, estimating their properties through indirect means, calculating their temperatures from theoretical models, detecting their transits by watching for the slight dimming they cause when passing in front of their stars. Until recently, that's essentially all we possessed in our toolkit. Transit signals, radial velocity measurements, gravitational microlensing events. The subtle dimming of starlight as a planet crosses in front of its host star became our primary detection method, accounting for thousands of discoveries. We found them through these techniques. We measured their orbital characteristics, determined their sizes, estimated their masses. The techniques proved effective, revolutionizing our understanding of planetary systems and revealing that worlds are common throughout the galaxy. But they remained fundamentally limited in what they could tell us. A silhouette reveals certain information about an object. Size, certainly. Orbital period, definitely. Rough mass if you combine it with radial velocity data. But it doesn't disclose the planet's detailed composition, what minerals form its surface, or what gases comprise its interior. It doesn't describe the chemistry of its atmosphere with any specificity, beyond perhaps the presence or absence of thick atmosphere. It certainly doesn't indicate whether biological processes might be operating there, whether anything lives on or within that world. Those deeper questions remain tantalizingly out of reach, frustratingly close, yet inaccessible. Webb transformed that limitation through its extraordinary infrared sensitivity. It created, for the first time, the genuine possibility of directly reading the chemical signatures embedded in an exoplanet's atmosphere. Not through indirect inference requiring extensive assumptions, not buried in noise, requiring sophisticated statistical analysis and careful modelling to extract, but directly, by separating the light that filtered through that alien sky during a transit and analysing its spectrum wavelength by wavelength, looking for the distinctive absorption features that different molecules imprint on starlight as it passes through them. That's how we achieved the first unambiguous detection of carbon dioxide on a world outside our solar system, a molecule we'd long suspected existed on hot Jupiters but had never definitively confirmed. WASP-39b, a scorching gas giant located 700 light-years distant. That single measurement validated the entire concept, proved that the technique worked as theory predicted. This wasn't promotional material anymore, not just promises from the mission team about what might be possible. Webb could genuinely read alien atmospheres, translating their chemical compositions into comprehensible data that atmospheric physicists could analyze and interpret. The discoveries accelerated rapidly from there as Webb turned its attention to more exoplanet targets. It identified water vapor signatures on WASP-18b, a planet so hot that water exists only as steam in its upper atmosphere. WASP-80b revealed similar signatures along with evidence of clouds and hazes. GJ486b, a super-Earth orbiting a red dwarf, showed possible signs of an atmosphere despite the intense radiation it receives. These aren't hospitable worlds by any stretch of imagination, not places you'd ever want to visit, even in a well-shielded spacecraft. One exists at temperatures that would vaporize lead and many other metals. Another orbits so close to its star that its year lasts mere days, with one hemisphere eternally facing the stellar inferno. But the significance isn't their habitability potential. The significance is our newfound ability to read them as individual worlds, to measure the density of their cloud layers, to track pressure variations throughout their atmospheres, to detect compounds like methane and sulfur dioxide, gases whose presence and ratios carry meaningful implications when they appear in specific combinations. Each molecule tells a story about temperature, pressure, chemistry, perhaps even geology if volcanic outgassing plays a role. Together, they paint a portrait of alien worlds more detailed than we ever imagined possible just a few years ago. Then came the observations of WASP-17b, where the findings took an unexpected turn that surprised even the scientists who'd been studying exoplanet atmospheres for decades. Webb didn't just detect vapors or common gases like those found on the other hot Jupiters. It identified solid particles suspended within the planet's atmosphere at high altitudes, far above where you'd normally expect particulates. Tiny crystalline silicates, essentially microscopic grains of quartz, circulating through the sky in perpetual suspension. Just as Earth's atmosphere can suspend water droplets, forming the clouds we see overhead, this world was circulating glass particles through its atmosphere like some cosmic hailstorm. Crystals formed from rock vapor that condensed at high temperatures. This marked the first time we'd observed such a phenomenon anywhere beyond our solar system, and it drove home a critical realization that planetary scientists are still absorbing. Exoplanets don't conform to Earth's atmospheric playbook. Their meteorological systems, their sky compositions, their fundamental physical processes might be radically, bewilderingly different from anything we experience on our home world. There might be planets with iron rain, worlds with ruby clouds, atmospheres that would seem like pure science fiction if we hadn't actually detected them. And Webb was the first instrument capable of actually revealing these alien realities in sufficient detail to understand what's happening. But the telescope's attention didn't remain fixed exclusively on distant worlds, orbiting other stars. Webb also directed its unprecedented capabilities inward, toward our own solar system, toward targets we'd been studying for decades or even centuries, but never quite seen with this combination of sensitivity and resolution. Even though these targets resided far closer than anything in the deep field images, separated by hours or days of light travel rather than billions of years, they still yielded surprises that reminded us how much we have yet to learn even in our own cosmic backyard. It captured the most detailed portrait of Neptune in over 3 decades, surpassing anything achieved since Voyager 2's historic flyby in 1989. Not merely the ring system, which appeared in exquisite detail with structures never seen before, but thermal mapping of the atmosphere, revealing temperature gradients and circulation patterns. The polar regions showing unexpected features. The structure of cloud formations at different altitudes and latitudes. The level of definition was extraordinary, transforming Neptune from a distant blue dot into a world with weather systems we could actually study and attempt to understand. Then it locked onto Chariklo, an unusual asteroid possessing its own miniature ring system, one of only a handful of minor bodies known to have rings. It detected water ice on its surface, mapping its distribution and abundance. That's an object spanning only a few hundred kilometers across, a tiny world by any standard, yet Webb could map its composition with enough precision to identify specific ices and estimate their abundance. It was a demonstration that the telescope's capabilities extended even to relatively small, faint objects if they fell within its observational range. It then observed Europa, one of Jupiter's numerous moons, and long considered one of the most promising places to search for life beyond Earth due to its subsurface ocean. Webb detected plumes of water vapor actively venting into space from surface cracks, material, erupting from the ocean beneath. This confirmed suspicions that originated from older missions like Galileo and Hubble, which had seen hints of this activity, but never with sufficient clarity to be certain. But this time the evidence arrived unambiguous, definitive. Europa wasn't merely an inert ice shell encasing a dead ocean. It was dynamically active, periodically ejecting material from its subsurface ocean like a cosmic geyser, providing potential access to that hidden ocean without even having to drill through kilometers of ice. And Webb was documenting it in real time, capturing individual eruption events. Even Comet 238P Reid, a small body in the asteroid belt, received scrutiny that revealed unexpected details. Webb detected water ice, but no carbon dioxide, an anomalous combination that immediately caught scientists' attention. Most comets display both signatures in roughly predictable ratios, both molecules frozen together in the comet's icy nucleus. This one didn't follow that pattern. That asymmetry provides clues about comet formation environments, about solar system chemistry, about how water molecules arrived in Earth's neighborhood originally and what processes shaped the early solar system. Either this comet formed in an atypically warm region where carbon dioxide couldn't condense, or its carbon dioxide sublimated away long ago when it passed closer to the Sun. Either interpretation adds detail to our understanding of these ancient remnants. Additionally, There were the trans-Neptunian objects, frozen remnants orbiting far beyond Pluto's domain in the Kuiper Belt and beyond, primitive bodies that have remained largely unchanged since the solar system's formation. Webb began identifying traces of methanol and organic molecular compounds on these distant ice worlds, complex molecules that shouldn't be there according to simple models. These compounds were helping astronomers reconstruct conditions in the outer solar system during its formation, understanding what chemical reactions occurred in that frigid environment and how organic molecules first formed in our cosmic neighborhood. These weren't static fossils simply preserved in ice. They exhibited chemistry, transformation, ongoing processes. They had their own narrative to tell about solar system history. So yes, James Webb was engineered to peer across vast cosmic distances to capture light from the dawn of time. But it proved equally powerful when examining nearby targets, when turning its golden mirrors toward familiar objects in our own solar system. Because every time it focused on something we believed we already understood adequately, whether a planet we'd previously discovered or a moon we'd been studying for decades with multiple spacecraft, it revealed something we'd overlooked, some detail that had escaped previous observations, some phenomenon that required us to revise our understanding even of worlds we thought we knew well. Throughout 2023, as Webb transitioned from its initial demonstration phase into full scientific operations, JWST began delivering data from extensive deep field surveys designed to push observational limits to their maximum. Among the first patterns astronomers noticed, a pattern that grew stronger with each new dataset, was the sheer abundance of galaxies appearing in observations covering the universe's first few 100 million years. Not merely faint smudges of light barely distinguishing themselves from background noise. Not possible contamination from foreground objects that needed careful filtering. Fully developed galaxies, dozens accumulating into hundreds, and eventually thousands in regions we'd assumed remained essentially empty during that epoch, still waiting for the first substantial structures to coalesce from the primordial gas, and some of them simply didn't fit existing models, no matter how astronomers tried to reconcile them with theory. Consider Sears 93316 as an example, one of the first candidates to generate serious discussion. Based on its calculated redshift, which measures how much the universe has expanded since the light was emitted, this galaxy appeared to exist merely 235 million years after the Big Bang. The most distant galaxy ever observed at that moment, pushing the observational boundary back to times previously inaccessible. That's dramatically earlier than we anticipated anything that's structurally complex could exist, according to models of galaxy formation that had been refined over decades. And it wasn't an isolated case, not some lone anomaly that could be dismissed as a measurement error or misidentification. Webb kept detecting similar objects as it continued its surveys. Luminous, compact, well-organized galaxies that didn't appear to be in formation, still assembling themselves from primordial material. They appeared completed, finished. Mature galaxies that looked like they'd already passed through the chaotic assembly phase and settled into stable configurations. That presented a significant problem because assembling a galaxy like that requires substantial time according to everything we understand about astrophysics. You need heavy elements beyond hydrogen and helium, the only elements created in the Big Bang itself. You need stars that complete their life cycles, passing through their main sequence and eventually exploding as supernovae that forge the heavier elements and disperse them into space. You need those elements to recycle into the next stellar generation, gradually enriching the gas and enabling planets and more complex chemistry. You need dust accumulation and gas dynamics and rotational momentum and gravitational orchestration all operating in concert across hundreds of millions of years of cosmic evolution. but these galaxies didn't possess that much available time according to our cosmological calendar. Something fundamental wasn't reconciling between theory and observation. Were these galaxies somehow fabricating stars through accelerated processes beyond anything we'd witnessed or could explain with known physics? Were they assembling through entirely different pathways, bypassing developmental stages we considered essential based on studies of galaxies in the modern universe? Or was our entire temporal framework for the early universe systematically incorrect by a significant margin, meaning our cosmic timeline itself needed major revision? Each possibility carried enormous implications that would ripple through multiple fields of astronomy. Then Webb uncovered something even more perplexing, a finding that challenged even more fundamental assumptions about the universe's large-scale structure. The JWST Advanced Deep Extragalactic Survey, abbreviated JADIS, one of the telescope's most ambitious deep-field imaging programs, concentrated on the Goods South and Goods North fields. These were regions of sky that had been studied extensively by previous telescopes, making them ideal for comparison and for pushing observations to greater depths with Webb's superior sensitivity. The program delivered extraordinarily detailed images of galaxies at extreme redshifts, galaxies from cosmic dawn that previous telescopes could barely detect. These observations were designed to refine our comprehension of galaxy formation mechanisms, to understand the physical processes that transform diffuse gas into organized stellar systems, and to illuminate how supermassive black holes achieved their enormous masses during cosmic dawn, a puzzle that has long challenged theorists. However, an unexpected discovery from JADIS data challenged foundational assumptions about the universe's structure that cosmologists had accepted for nearly a century. Specifically, it questioned the principle of isotropy, the cosmological principle asserting that the universe should appear essentially identical in all directions, exhibiting no preferred orientation or rotational bias. This principle forms one of the foundations of modern cosmology, underlying our standard models of cosmic evolution and structure formation. If it's wrong, if the universe does have a preferred direction or rotation, many of our conclusions need re-examination. In research led by Lior Shamir of Kansas State University, investigators analyzed 263 spiral galaxies in the Goods South field using sophisticated algorithms that assess galactic spin direction from radial intensity distributions in the images. The software examined how light is distributed in each galaxy, looking for the patterns that indicate whether a spiral galaxy is rotating toward us or away from us, essentially determining which way the spiral arms are trailing. The results revealed a striking asymmetry that immediately caught attention. 158 galaxies, representing 60% of the sample, rotated clockwise from Earth's perspective. 105 galaxies, representing 40%, rotated counterclockwise. In a truly isotropic universe, you'd expect a roughly 50-50 split, maybe 51-49 or 52-48 due to statistical fluctuation, but not 60-40. That level of imbalance, while not overwhelmingly large, was statistically significant given the sample size. It suggested a possible preferred spin direction in this spatial region, directly challenging the concept of a directionless, homogeneous universe. If confirmed with larger samples, this could indicate that the universe has some large-scale rotational component, that space-time itself might carry angular momentum from the Big Bang or from some earlier process. Previous studies had noted similar spin asymmetries in different galaxy samples, so this wasn't entirely unprecedented, but the effect appearing in Webb's data made it harder to dismiss as instrumental bias or selection effects. The pattern appeared more pronounced at higher redshifts, at greater distances corresponding to earlier cosmic times, implying that if real, this might represent a primordial structure embedded in the cosmos itself, perhaps imprinted during the first moments of inflation or even before. Some researchers speculate this might align with physicist Nikodem Poplawski's unconventional theory, proposing our universe formed within a rotating black hole in a parent universe, potentially imparting a directional spin bias to cosmic structures as they formed. It's a highly speculative idea, far outside mainstream cosmology, but the observations at least make it worth considering. However, Shamir's research team offered a more conventional explanation that doesn't require exotic physics or overthrow existing cosmology. The asymmetry might stem from Doppler effect bias, an observational selection effect rather than a property of the universe itself. The Milky Way's motion through space at hundreds of kilometers per second could make galaxies spinning opposite to our perspective appear slightly brighter due to blue shift as they rotate toward us, while galaxies spinning away would be slightly redshifted. This brightness difference, though subtle, could potentially skew automated classification systems that identify spiral direction based on arm brightness. The software might be more successful at identifying galaxies spinning one direction than the other simply because they're slightly easier to see. The limited sample size of 263 galaxies, while respectable for such a study, and the inherent challenges of imaging faint, high redshift objects, urge appropriate caution before drawing firm conclusions. Larger, more diverse datasets from ongoing JWST observations will prove crucial in determining whether this asymmetry reflects genuine cosmic structure or merely an observational artifact that will disappear with better data. It's exactly the kind of intriguing puzzle that requires more work to resolve conclusively. Compounding these challenges to cosmological models, JD's also revealed galaxies with redshifts exceeding 13, corresponding to times when the universe was younger than 330 million years. These galaxies, far from being weak protostructures barely distinguishable from background noise, are luminous, compact, and surprisingly mature in their properties. A standout example, JDAR's GS Z13-0, with its extreme redshift placing it among the most distant objects ever observed, has forced astronomers to reconsider how early galaxies could collapse from primordial gas clouds in such abbreviated timeframes. Typically, such collapses demand extended periods. Gas must cool enough to allow gravity to overcome thermal pressure. Density fluctuations must grow through gravitational instability. The first stars must form and begin illuminating their surroundings. All these processes take time according to our models, yet these galaxies appear fully formed, already containing substantial stellar populations within the universe's first 300 million years. They're not showing signs of ongoing assembly. They look complete, as though they'd been around far longer than the universe's age allows. This isn't an isolated anomaly that might be explained away as unusual circumstances. It's emerging as a consistent pattern across multiple deep field observations. These ancient galaxies weren't merely existing in some primitive state, barely clinging to existence in a harsh early universe. They were thriving, actively manufacturing stars at rates that seem incomprehensible given the limited raw materials available at that epoch. The universe at 300 million years hadn't yet produced many heavy elements. Almost everything was still hydrogen and helium from the Big Bang. Yet these galaxies were forming stars prolifically, far faster than models predicted they should be able to given the available ingredients. It resembled watching a tiny campfire inexplicably transform into a massive conflagration despite having access to only a handful of kindling, with no additional fuel source apparent. The energy output, the star formation rates, the sheer luminosity didn't match what should be possible with the materials at hand. Some astronomers began calling it the too early, too big problem, a catchy phrase that captures the essence of the puzzle. The galaxies were excessively massive for their age, excessively luminous given their expected stellar populations, appearing excessively soon in cosmic history according to every timeline we'd constructed. So what's actually happening? What physical processes could explain these observations without completely overthrowing fundamental physics? One possibility is that star formation in the primordial universe operated with dramatically higher efficiency than contemporary models predict. Perhaps conditions prevalent then, involving higher densities as the universe was smaller, more frequent galactic collisions as objects were closer together, and different chemical compositions with almost no heavy elements to radiate energy away, enabled galaxies to expand and form stars at accelerated rates compared to what we see today. The physics might be the same, but the initial conditions so different that the outcomes look nothing like modern galaxy formation. Alternatively, our models might be missing some critical physical ingredient, some process or mechanism we haven't incorporated yet because we didn't know it was important, or because we haven't discovered it. Perhaps an unknown cooling mechanism that allows gas to collapse faster than we thought possible. Perhaps a gravitational effect we haven't accounted for that accelerates structure formation. Perhaps something about dark matter's behavior in the early universe that differs from its behavior today. Any of these could potentially explain the observations if we could just identify what we're missing. Another hypothesis gaining attention suggests these galaxies form through direct collapse rather than the gradual hierarchical assembly we normally envision. Instead of slowly accumulating stars and building mass incrementally over hundreds of millions of years, perhaps some galaxies collapsed almost instantaneously from dense gas clouds, forming massive stellar populations and possibly central black holes in a single, rapid, chaotic event. Think of it as the difference between building a house brick by brick versus having the entire structure suddenly appear fully formed. If that's accurate, it could also explain how some of the earliest quasars, those extraordinarily bright beacons powered by actively feeding black holes, came to exist so prematurely when conventional formation scenarios suggest black holes shouldn't have had time to grow so large. But here's the complication that keeps theorists awake at night. The more we attempt to explain these observations, the more intricate and interconnected the picture becomes. Because every time Webb examines those early epochs with its unprecedented sensitivity, it discovers more galaxies displaying these properties, not fewer. More luminosity when we expected, objects to be faint and struggling, less chaos when we anticipated disorder and randomness, more structural organization when we predicted primitive, irregular systems. The problem isn't going away with more data. If anything, it's becoming more pronounced, more difficult to explain away as observational errors or selection effects. Astronomers now face a more profound question that cuts to the heart of our understanding. What if the early universe was never the quiet, gradually awakening place we imagined based on extrapolations from late-time observations? What if everything, stars, galaxies, black holes, large-scale structure, came online faster, louder, more vigorously than we ever conceived possible from our comfortable position 13.8 billion years later? What if the infant universe was actually more dynamic, more energetic, more productive than the mature universe we observe today? If that's true, and the evidence increasingly suggests it might be, then the universe isn't just older than some of our estimates suggested, though that may be part of it. It's fundamentally busier in its youth, more aggressive in its structure formation, more intensely alive even during its supposed infancy than our smooth, gradually evolving models predicted. It suggests the early universe was a far wilder place than we imagined, where processes we think take billions of years somehow occurred in mere hundreds of millions. And all these timeline-shattering findings, every one of these galaxies that shouldn't exist yet, emerged from just the first year of Webb's deep field investigations. The early science results, as impressive as they are, we're barely beginning to scratch the surface of what this telescope will ultimately reveal as it continues operating, hopefully for decades, continuing to push deeper and see further back in time. The moment we identified galaxies that were excessively large for their age, an immediate corollary question emerged that had been lurking in the background. If these galaxies achieved such massive scale this early in cosmic history, where are the supermassive black holes that should have evolved alongside them? That relationship between galaxies and their central black holes has been well established in the modern universe, but its origin remains mysterious. That's been a persistent puzzle in astronomy for decades now. We know from extensive observations that most large contemporary galaxies harbour a supermassive black hole at their core, sometimes billions of times more massive than our Sun, with masses correlated to properties of their host galaxies. But we still lack definitive understanding of their formation mechanisms, how they came to be, and how they achieved such enormous masses. Do they originate as stellar mass black holes, the remnants of massive stars, that gradually accumulate material over eons through steady accretion? If so, the math doesn't quite work out. Growing a billion solar mass black hole from a stellar remnant of perhaps 30 solar masses requires consuming enormous amounts of material, and there are physical limits to how fast accretion can occur. The process would take many billions of years at the maximum accretion rates allowed by physics. But we see billion solar mass black holes existing when the universe was less than 1 billion years old. There simply hasn't been enough time for them to grow from stellar seeds through normal accretion. Or do some black holes simply manifest already enormous, born massive, through some different formation channel? That's been proposed, but seemed physically difficult to achieve. Until recently, we didn't have observational evidence one way or another, because we couldn't see black holes from the early universe directly. They're dark by definition, and only become visible when actively feeding on surrounding material and glowing brightly as quasars. James Webb didn't definitively resolve that fundamental question, but it delivered something we didn't anticipate: observations that opened a new window on the problem. Proof that these cosmic monsters were already present and already active in the early universe, already feeding and growing when they theoretically shouldn't have had time to form. One of the most significant surprises originated from a galaxy designated Sears 1019, one of many targets in Webb's deep field surveys that might have gone unnoticed in the deluge of data, except for one remarkable characteristic. It's distant and faint, exactly the kind of object that would have been impossible to study in detail with previous telescopes. But when Webb examined it closely with its full suite of instruments, it detected an unmistakable signature that immediately caught researchers' attention. The characteristic spectral fingerprint of an active galactic nucleus, those distinctive emission lines that can only be produced by gas heated to millions of degrees as it swirls toward a central black hole. This confirmed a central black hole actively consuming surrounding material, pulling in gas and stars and whatever else strays too close. Not simply existing dormant at the galaxy's heart, not patiently waiting for material to drift in. Actively feeding, growing, radiating tremendous energy that makes the galactic nucleus brighter than billions of stars combined. That's critically important because Sears 1019 doesn't reside in the modern universe where we're accustomed to finding such objects. This isn't a quasar from 1 billion years ago, which would already be surprising. Its light departed when the cosmos was merely about 570 million years old, less than 4% of its current age. So how did a black hole, even a relatively modest one compared to the giants we see today, form, accumulate substantial mass, and begin actively accreting matter that early in cosmic history? According to standard formation models, all of which have been carefully developed and tested against observations of nearby black holes, that's not supposed to occur on such short timescales. Black holes in those models require raw material to form initially. They need sufficient mass concentrated in a small enough region for gravitational collapse to occur. They need stars to complete their cycles and die, either exploding as supernovae or collapsing directly if massive enough, leaving behind stellar mass black holes. They need galaxies to evolve and mature, developing the dense nuclear regions where black holes can grow efficiently by consuming the concentrated gas. All these processes demand substantial time, far more than 570 million years by conventional estimates. But this black hole, and several others like it that Webb has discovered, appeared to circumvent that timeline entirely, skipping steps that we thought were essential. They're simply present already at this early epoch, already operational and feeding, already glowing as active galactic nuclei. Either they formed extraordinarily fast through mechanisms we don't understand, or they started out much larger than stellar mass black holes, or our timeline for these processes is fundamentally wrong. None of these options are particularly comfortable for theorists. That observation led researchers to revisit a controversial hypothesis that had been around for years but lacked observational support: the concept of direct collapse black holes. The basic concept proposes that instead of forming from stellar remnants that gradually grow through accretion, some black holes might form directly from massive gas clouds collapsing under their own immense gravity before a single star ever ignites within them. Under special conditions, if the gas can't cool efficiently and fragment into stars, it might collapse as a whole directly into a black hole of perhaps tens of thousands of solar masses or more, skipping the stellar phase entirely. It's chaotic and requires very specific conditions to occur. The gas cloud must be massive, hundreds of thousands or millions of solar masses. It must be hot enough that it can't fragment into stars, but not so hot that thermal pressure prevents collapse. It needs to avoid being polluted by heavy elements from earlier stars, which would allow more efficient cooling. If all those conditions align, perhaps during the universe's first few 100 million years, you might get direct collapse creating intermediate mass black holes that can then grow to supermassive status much faster than starting from stellar masses. It's messy and not fully understood theoretically, but it might explain how black holes could be born already massive, born with a significant head start on their growth toward billions of solar masses. And once they achieve significant mass through whatever formation channel, they don't remain quiet if material is available. That's where quasars enter the picture, those brilliant beacons that are among the most luminous objects in the universe. Webb began identifying quasars, systematically, incredibly bright objects powered by black holes voraciously consuming matter at enormous rates, from distances exceeding 13 billion light-years, corresponding to times less than a billion years after the Big Bang. These aren't rare finds anymore with Webb's sensitivity. They're accumulating in surveys showing that luminous quasars were more common in the early universe than we realized. One such quasar in a galaxy designated J0439+634 exhibited light so severely distorted and amplified that it could only be explained through gravitational lensing, the same phenomenon we discussed earlier. A giant foreground galaxy cluster was bending the quasar's light across space according to Einstein's predictions, creating multiple magnified images and allowing Webb to study this incredibly distant object in detail that would otherwise be impossible. That's more than merely a fascinating optical effect, though it certainly is that. It's an observational window into the deep past that effectively gives us a more powerful telescope for free. Lensing captures objects that would normally be impossibly faint at the very edge of detectability and stretches them across the sky while magnifying their brightness. It reveals structural details we shouldn't theoretically be able to resolve given the angular sizes involved. And it operates bidirectionally in a sense. We can study both the lensing object in the foreground and the lensed background object simultaneously, learning about both systems. One of the most compelling examples of gravitational lensing's power occurred in September 2023, when astronomers using Webb's data detected a supernova, a dying star's explosive death throes that had been triply lensed by a massive galaxy cluster positioned between us and the supernova. It was nicknamed SN-H0PE, a playful reference both to HOPE and to the Hubble constant H0 that describes cosmic expansion. The same explosion appeared in 3 separate locations on the sky. Simultaneously, like a cosmic magic trick, each image slightly offset in time due to the different path lengths light travelled through curved space-time to reach Earth. Think of it as a cosmic time lapse, a natural consequence of general relativity's predictions. The identical explosion replaying through different routes in space, each route with a slightly different length, causing the images to arrive at different moments separated by days or weeks. That's more than just intellectually fascinating for physicists who appreciate general relativity's successful predictions. It's observationally valuable for cosmology, providing a completely independent way to measure cosmic expansion. By measuring the time delays between each image's appearance with high precision, by watching how the supernova brightens and fades in one image and then repeats that light curve in another image days later, astronomers can actually employ lensed supernovae to calculate the universe's expansion rate with remarkable precision. The time delays depend on the expansion rate, so if you can measure them accurately enough, you can determine H0, something we've been debating intensely for years because different measurement methods keep giving slightly incompatible answers. There's an ongoing controversy called the Hubble tension, a genuinely puzzling discrepancy in modern cosmology. The persistent problem is that our 2 best independent methods for measuring cosmic expansion, one based on the cosmic microwave background from the early universe, the other based on supernova and other distance indicators in the modern universe, yield answers that differ by about 10%. That might not sound like much, but it's statistically significant given how precisely we can make these measurements. Either one method has systematic errors we haven't identified, or something interesting is happening in cosmic expansion that we don't understand, or possibly our cosmological model needs modification. But lensed supernovae like SN-H0PE offer a third independent measurement technique that doesn't rely on the same assumptions as either previous method. And Webb's extraordinary sensitivity makes it possible to detect them early in their light curves, even when they're extremely faint, and to catch all multiple images before they fade. So while it's out there spotting galaxies and black holes that theoretically shouldn't exist yet, according to standard models, it's also quietly contributing crucial data toward resolving, or perhaps complicating further, one of cosmology's most heated debates. The beauty is that the telescope simply observes and reports what's there. It's up to us to figure out what it all means. But then Webb discovered something even stranger, another class of objects that challenged our understanding in a different way. It began detecting galaxies that were no longer manufacturing stars despite their youth. Not millions of years into cosmic history, which might be understandable, but within the first billion years, when galaxies should theoretically be at peak star formation, burning through their gas supplies and building stellar populations. These weren't galaxies just beginning their evolutionary journey, systems in the midst of assembling their first stellar generations. They were already silent, finished with star formation, done, as though they'd ignited briefly in a burst of activity, burned intensely through their available gas, and then simply ceased all star formation entirely. That's not supposed to happen according to standard models of galaxy evolution either, adding another puzzle to the growing list. Galaxies are expected to experience an extended chaotic adolescence lasting billions of years. Stars forming continuously as gas clouds collapse. Dust and gas swirling turbulently as gravitational instabilities ripple through galactic disks. Violent processes occurring throughout as supernova shockwaves trigger new star formations. even as they disrupt other regions. It's supposed to be messy, prolonged, energetic. The transition to quiescence, to a red and dead galaxy that's exhausted its gas and stopped forming stars, is expected to take billions of years and occur primarily in the modern universe. But these galaxies, observed just 700 million years after the Big Bang when found, were already quiescent according to spectroscopic analysis. That's the technical terminology, meaning no new stars forming, no available gas left to fuel further stellar production, all the stars already formed and now just aging. It's analogous to discovering an elderly individual in a kindergarten classroom, someone who's somehow already lived a full life when they should just be starting out. You simply don't expect to encounter something that evolved that early, that far along its evolutionary path when the universe has barely begun. But Webb found them, and not as isolated cases that might be dismissed as flukes. Multiple examples in different survey fields, suggesting this might be a more common phenomenon than anyone suspected. They're now being called sleeping beauty galaxies in the scientific literature. Catchy terminology, bizarre reality, because we still don't comprehend why they ceased star formation so prematurely. Did they consume all their gas in an initial burst and have no way to acquire more? Did some process heat or expel the remaining gas, preventing further collapse? Are they truly dead, or might they potentially reawaken if they acquire new gas through interactions with other galaxies? But it's increasingly clear that star formation, like galaxy assembly and black hole genesis, doesn't follow one simple universal rulebook that applies everywhere and at all times. The universe's behavior in its youth appears qualitatively different from what we observe today in mature galaxies. The physics is presumably the same, but the conditions and available ingredients are different enough that outcomes vary dramatically. For an extended period during Webb's first year of operations, the telescope's discoveries centered primarily on what we didn't anticipate, on findings that challenged existing models. Galaxies appearing too soon in cosmic history, black holes growing too large too quickly, stars forming too rapidly given available materials, structural maturity appearing far earlier than theory predicted, each finding fascinating in itself, each requiring explanation, each suggesting our models needed revision or extension. But in early 2025, something shifted in the scientific conversation surrounding Webb. The focus transformed from questions of structure and chronology to perhaps the most profound question humanity can ask. The conversation began to center on the possibility of life itself existing beyond Earth, not as speculation, but as something we might actually detect through atmospheric chemistry. The catalyst was a planet designated K2-18b, a world located approximately 120 light-years away, orbiting a cool dwarf star in the constellation Leo. Close enough to study in detail, far enough that we'd never physically visit with current technology. We'd known about K2-18b for several years before Webb's launch. Previous telescopes, particularly Hubble Space Telescope, had detected hints that it might possess water vapor in its atmosphere, spectral features suggesting H2O molecules absorbing certain wavelengths of light during transits. That alone generated substantial interest in the planetary science community. Not Earth-like by any means, it's significantly larger and more massive than Earth, but positioned in what's loosely termed the habitable zone around its star, that orbital region where temperatures could potentially allow liquid water to exist on a surface or in clouds. Not excessively hot like the hot Jupiter's Webb had been studying. Not excessively cold like Neptune. Potentially just right for liquid water, though with many caveats about atmospheric composition and pressure. But Webb detected something beyond water vapor when it turned its far more sensitive instruments toward this interesting world. In April 2025, after months of careful analysis and verification, scientists announced they had identified dimethyl sulfide, abbreviated DMS, in the planet's atmosphere at a statistically significant level. This announcement sent ripples through the scientific community because of what DMS represents on Earth. This particular molecule, this specific arrangement of carbon, hydrogen, and sulfur atoms, is exclusively produced by biological activity on our planet, specifically by marine phytoplankton and certain types of algae, microscopic organisms that release DMS as a metabolic byproduct. No volcanic processes that we know of produce DMS in detectable quantities. No lightning discharges create it. No abiotic chemistry we've documented in laboratory settings or observed in nature generates it without biological involvement. On Earth, DMS is a biosignature, a chemical that reliably indicates life's presence. However, and this is critical to understand, scientists appropriately caution that unknown non-biological processes might exist that we haven't characterized yet. Photochemical reactions in hydrogen-rich atmospheric environments could potentially produce DMS through pathways we haven't explored because we've never encountered such conditions. The chemistry might work differently under conditions completely unlike Earth. It's essential to maintain appropriate caution here, to not get ahead of what the data actually tells us. This isn't confirmation of extraterrestrial life, despite what some headlines might suggest. It's not definitive proof of anything. The spectral signal isn't yet strong enough, the statistical confidence not yet high enough to constitute detection beyond all reasonable doubt that would satisfy the extraordinary evidence required for such an extraordinary claim. But the statistical confidence level is high enough to warrant serious attention from the scientific community, high enough that this isn't just noise or instrumental artifact. Some estimates from the research team place the confidence around 99.7%. Not absolute certainty, not proof, but far exceeding the level of random background noise or measurement error. Webb didn't merely detect a possible DMS signal in isolation either, which would be more ambiguous and easier to explain away. It also identified methane at substantial concentrations, carbon dioxide as expected, and indications of dimethyl disulfide, another sulfur-containing organic molecule. All molecules that, in the appropriate combination and ratios, could potentially indicate biological processes rather than purely abiotic chemistry. The pattern matters as much as any individual molecule. On Earth, life produces specific combinations and ratios of gases that are thermodynamically improbable in the absence of biology, that wouldn't persist in equilibrium without continuous biological production. And K2-18b isn't a gas giant like Jupiter or Saturn where we'd never expect life to exist. It's not a rocky Earth-like world either. It's classified as a Hycean world, a planet category hypothesized to be common in the galaxy, but which we're only now beginning to characterize observationally. Somewhere between a super-Earth and a mini-Neptune in size and mass. A water-rich world with a thick hydrogen-rich atmosphere, possibly harboring a global ocean beneath dense cloud layers, an ocean that might be hundreds of kilometers deep, covering the entire planetary surface. Imagine an ocean world with no continents, no land masses, potentially habitable for aquatic life forms if conditions are right. That combination of environmental conditions, liquid water, organic molecules, appropriate temperatures, methane, carbon dioxide, and now possibly DMS, is unusual to say the least. Not impossible. Theoretically with sufficiently exotic abiotic chemistry, but statistically improbable without something living contributing to the atmospheric mix, without biology actively producing and maintaining chemical disequilibrium. It's the kind of combination that makes astrobiologists sit up and take notice, that warrants extensive follow-up observations to characterize more precisely. Naturally, Scientists debate the interpretation vigorously. They continue debating it actively across conferences and journal papers. Could exotic photochemistry in a hydrogen-rich atmosphere generate this signature through purely abiotic processes? Could some process we don't yet understand, some chemical pathway not yet explored in laboratories, be responsible without requiring biology? Possibly. We don't know every possible chemistry that can occur under every possible set of conditions. There's still much to learn about atmospheric chemistry on worlds vastly different from Earth. But that's precisely what makes this observation scientifically important rather than merely interesting. It raises a genuine, testable question that can be answered through further observations. Is this chemistry biological in origin, or can it be explained abiotically? We can test this through additional spectroscopy with Webb and eventually with future telescopes. We can look for other biosignature combinations. We can search for seasonal variations that might indicate biological cycles. We can compare K2-18b's atmosphere with similar planets to see if this pattern is unique or common. And it's the first time we've obtained such intriguing data from a planet beyond our solar system that genuinely raises the question of life, not as speculation, not as remote possibility, but as genuine hypothesis requiring testing. No artist's interpretation needed, no speculative theory requiring assumptions about how life might work elsewhere. Just observational data requiring explanation, chemical signatures that demand interpretation. And while headlines understandably emphasize the signs of life angle, playing up the possibility because it captures public imagination, the genuine value remains quieter for scientists, more fundamental to the practice of science itself. Webb is finally providing what the scientific community needs to transform astrobiology from theoretical speculation into observational science. Concrete clues, not imaginative stories. Measurable signals, not speculative narratives. Data that can actually be tested and refined with future observations. This represents exactly the kind of science Webb was built to enable. Not providing definitive answers immediately, which would be unrealistic given the challenges involved, but raising questions that can actually be answered through continued observation, through accumulation of better data, through comparison between multiple worlds, showing which features are common and which are rare. That's how science progresses, not through sudden revelations, but through careful accumulation of evidence that gradually transforms our understanding. But that wasn't the only milestone Webb achieved during this remarkable period of discoveries. In May 2025, just weeks after the K2-18b announcement, astronomers confirmed detection of the most remote galaxy ever observed by humanity, a record that keeps getting pushed back as Webb continues its surveys. A compact luminous object designated JDES-GS Z14-0 based on the survey that found it. Its redshift was calculated at approximately Z equals 14.32 through careful spectroscopic analysis, meaning the light we're now detecting departed that galaxy over 13.5 billion years ago when the universe was merely 280 million years old, less than 2% of its current age. Let that temporal scale register for a moment. We're now observing galaxies that existed when the cosmos was in its infancy, when the first stars had just ignited, when the universe's structure was just beginning to emerge from initial density fluctuations. These galaxies formed from essentially pristine gas, almost pure hydrogen and helium, containing virtually no heavy elements because no previous stellar generations had existed to create them. This is as close as we can currently observe to cosmic dawn, to the moment when darkness ended and light began. JDES-GS Z14-0 isn't a massive system comparable to the Milky Way's 200 billion stars. It's actually quite small, perhaps a few billion stars at most. But it's intensely bright for its size, experiencing vigorous star formation at rates disproportionate to its mass. The stars are hot, young, burning intensely. This is a galaxy at the beginning of its evolutionary journey, and we're witnessing it at that moment. But it's real, and it's not solitary. Webb's systematic deep field investigations have identified dozens of similar candidate galaxies at these extreme distances, all awaiting spectroscopic confirmation, systematically filling in the observational gaps of an epoch we've never truly witnessed before, except in theory and simulation. With each new deep field, with each additional survey, more galaxies appear at these incredible distances. The universe's first billion years, once a complete mystery accessible only through computer simulations, is now becoming an observational domain we can study directly. Every new galaxy provides constraints for theoretical models, helps us understand how structures first formed, tests predictions about the initial conditions encoded in the cosmic microwave background. It's cosmic archaeology, reconstructing the universe's history from the fossil record of ancient light. Then arrived one of the most visually striking surprises in recent memory, an image that captured public imagination even as it provided genuine scientific value. In July 2025, the James Webb Space Telescope captured an extraordinary image of two galaxies caught in mid-collision, forming a system that astronomers dubbed the Infinity Galaxy based on its remarkable appearance. When the raw data was processed and enhanced, applying techniques to bring out faint features and structural details, the combined morphology resembled a near-perfect infinity symbol, that sideways figure 8 that mathematicians use to represent endlessness. A beautiful configuration of stars, gas, and gravitational interactions, two galactic disks wrapping around each other in a cosmic dance that will ultimately merge them into one. Astronomers were initially captivated by its striking visual appearance. The geometry was almost too perfect, like something designed rather than naturally formed. But the authentic scientific value lay deeper than the aesthetics, hidden in the physics driving this cosmic collision. The shape attracted substantial attention, undeniably generating widespread sharing on social media and public interest in astronomy. But the genuine discovery wasn't the symbolic geometry that made for compelling images. It was what was concealed at the system's heart, what the collision was producing in the dense region where the two galactic nuclei were beginning to interact. Between the two colliding galactic nuclei, hidden in the dense gas clouds being compressed by the collision's gravitational forces, researchers identified a supermassive black hole actively feeding on the collision's debris. Not just existing passively, but actively pulling in material and accumulating mass at prodigious rates as the collision funnels gas toward the center. Based on its luminosity, its energy output across multiple wavelengths, and particularly the extreme gas densities present in the collision zone providing raw material for rapid growth, there's a compelling possibility this represents something extraordinary. This might be a direct collapse black hole in formation, that rare phenomenon where a massive gas cloud collapses directly into a black hole without forming stars first, creating an intermediate mass black hole that can then grow rapidly to supermassive status. This could provide a critical observational clue, perhaps the best direct evidence yet, to one of astrophysics' most persistent mysteries that we discussed earlier. How do supermassive black holes expand from essentially nothing to billions of solar masses in relatively brief cosmic timescales? How did they grow so large so quickly in the early universe? If we're witnessing direct collapse occurring, if this process is indeed creating black holes that start out massive rather than building up from stellar remnants, it would help explain the timeline problem that has puzzled theorists for decades. The Infinity Galaxy, observed as it existed approximately 7.5 billion years ago when the universe was roughly 6.3 billion years old, isn't from the earliest cosmic epochs like the JD's galaxies we discussed, but it offers a vivid snapshot of the chaotic mergers that sculpt galaxies and their central black, holes throughout cosmic history, processes that shape galactic evolution and build the structures we see today. More than a stunning image suitable for framing, it functions as a natural laboratory for studying the physical processes that drive formation of the universe's most massive objects, illuminating how collisions in extreme environments can trigger rapid black hole growth through mechanisms we're only beginning to understand. We've been detecting exoplanets for nearly 3 decades now, since the first confirmed discoveries in the 1990s revolutionized planetary science. Throughout that entire period, across thousands of planetary discoveries, we've primarily identified them through indirect inference rather than direct observation. Monitoring how starlight diminishes during transits, measuring how stars wobble due to orbiting planets' gravitational pull, occasionally detecting gravitational microlensing events, all indirect methods that revealed planets' existence without actually seeing them. It's proven remarkably effective at finding planets, enabling the discovery of over 5,000 confirmed worlds so far. But it's never genuinely felt like seeing a planet in the way we think of seeing objects. It's more analogous to watching a shadow's movement and attempting to deduce what cast it, inferring properties from secondary effects. So when the James Webb Space Telescope captured its first direct image of an exoplanet, actually photographing the planet itself rather than detecting its effects, it wasn't merely a technical milestone, it was a fundamental shift in how we study distant worlds, a transition from inference to observation, from shadows to reality. It occurred in September 2022, during Webb's first few months of science operations while the mission team was still exploring the telescope's capabilities. The planet, designated HIP 65426b, hadn't been the subject of major headlines previously. One of the quieter targets, interesting to specialists, but not widely known to the public. Orbiting a faint star approximately 350 light-years distant, far enough that we'll never visit, but close enough for detailed study. Not Earth-like by any measure, not a candidate for harbouring life, just a massive gas giant several times Jupiter's mass. Precisely the type of planet that's easier to image directly because it's large, intrinsically bright in infrared wavelengths due to its residual heat from formation, and orbits far enough from its star, about 100 times Earth-Sun distance, to avoid being overwhelmed by stellar glare that normally drowns out planetary light. But those characteristics made it the ideal test subject for demonstrating Webb's direct imaging capabilities. Using its coronagraph, a device specifically engineered to block a star's overwhelming light, Webb successfully isolated the faint glow of the planet itself, shining in reflected and thermal emission. Not a shadow, not a spectral trace embedded in starlight. Actual photons emitted and reflected from the planet's atmosphere, captured and analysed in exquisite detail across multiple infrared wavelengths simultaneously. That light revealed atmospheric temperature through thermal emission, cloud composition from spectral features, molecular fingerprints from absorption lines. It confirmed methane at high altitude, detected water vapour deeper in the atmosphere, even suggested deeper structures within the cloud layers, phenomena like vertical temperature gradients, pressure variations with altitude, and haze distribution affecting visibility. And for the first time in exoplanet science, scientists could examine a planet in another stellar system as a genuine world with its own directly observable characteristics, not merely a data point on a graph or an entry in a catalogue. Not an inference from transit depth or radial velocity amplitude, but an actual image showing where the planet is relative to its star, how bright it appears, how its spectrum reveals composition. This represented a fundamental methodological shift. Naturally, this kind of direct imaging isn't theoretically novel as a technique. A few ground-based telescopes, particularly large facilities like Keck, Gemini, and the Very Large Telescope with adaptive optics systems have accomplished direct imaging under highly specific conditions for the most favorable targets. But those images were faint and noisy, barely sufficient to determine what you were observing, requiring extensive image processing to extract planets from the stellar glare. Spectroscopy was limited to the brightest cases. This Webb image arrived qualitatively different, clean, high resolution, detailed enough to analyze what the atmosphere was actively doing, not just catalogue what molecules it contained. Multiple wavelengths simultaneously providing temperature maps and compositional information. It marked the first occasion where the distant glow of a world beyond our solar system could be treated as authentic direct imaging data comparable to what we obtain from solar system planets, not merely a suggestion or statistical inference from indirect methods. The planet appeared as an actual point of light separated from its star, something you could point to and say, "There's the planet," rather than inferring its presence from subtle effects. And now that Webb has demonstrated this capability and refined the techniques, the possibilities have dramatically expanded for studying exoplanets through direct imaging. Planets like HR 8799c, Beta Pictoris b, and eventually the smaller, cooler ones, the more Earth-like worlds we genuinely want to understand, are now becoming accessible to direct observation, gradually, meticulously, requiring careful planning and long exposures, but for the first time visibly as actual objects we can photograph and study. And again, this wasn't promotional hype or speculative promises about future capabilities. There was no elaborate countdown, no extravagant press conference with politicians and celebrities. The data was released through standard peer-reviewed studies in astronomical journals where experts could examine the methods and verify the results. And the image, while superficially simple, just a dot of light near a brighter star, carried the full weight of 2 decades of engineering innovation behind it, representing the culmination of countless technical challenges overcome. This is how major scientific progress manifests now in the 21st century. Quiet, technical, measured, carefully verified, but absolutely undeniable once confirmed. While Webb was accomplishing that landmark direct imaging, it also directed attention toward objects considerably closer to home. Objects traversing our own cosmic neighborhood, things moving through our solar system right now. Objects like Asteroid 2024, YR4, one of countless small bodies, but one that happened to be in the right place at the right time for Webb to observe. This was a near-Earth object, an asteroid whose orbit brings it relatively close to our planet, roughly the size of a 15-story building. Not large enough to be a headline generator, not on a collision course, not an impact threat requiring planetary defense, but still scientifically worthy of examination because small, rapidly moving asteroids prove difficult to observe comprehensively with conventional telescopes. They move quickly relative to background stars, making long exposures challenging. They reflect minimal sunlight due to their small size. They typically pass by with only a brief visibility window before moving too far away or into unfavorable viewing geometry. So characterizing them, determining their composition and exact orbits, requires capable instruments and prompt observations. Webb managed all of this despite being designed primarily for distant targets. Webb intercepted the asteroid as it passed through its field of view, tracked its trajectory across the sky, measured its surface composition through spectroscopy, revealing what minerals comprised its surface, determined its precise orbital characteristics through position measurements over time. It even contributed data to refining risk assessment models for lunar impacts, as this particular asteroid had a low probability impact window for the Moon due to complex gravitational interactions with Earth that could potentially alter its orbit over time. Low probability, but non-zero, making it worth tracking carefully. It wasn't spectacular science, wouldn't make headlines or change our understanding of the universe. But it mattered because it demonstrated that JWST isn't merely proficient at peering into the deep past toward cosmic dawn. It's equally capable at scanning nearby space with unprecedented detail, even when the object is small, dim, and moving rapidly. Even when the target is fundamentally different from what the telescope was primarily designed to observe. That versatility proves valuable for numerous science cases beyond the headline-grabbing discoveries. And that's part of the authentic narrative here that sometimes gets lost in discussions of Webb's spectacular deep-field images. Everyone conceptualizes Webb as the deep universe machine, the time machine that lets us look back toward the Big Bang. And it absolutely is that. But its infrared sensitivity, precision tracking capabilities through sophisticated guide star sensors, and spectral resolution across multiple instruments have rendered it valuable for everything from icy moons in our outer solar system to dusty comets passing through the inner solar system to active asteroids and beyond. It's not a single-purpose telescope despite popular perception. It's a comprehensive toolbox capable of addressing diverse questions across multiple fields. And the questions it's helping answer, from atmospheric chemistry on exoplanets to orbital dynamics of near-Earth asteroids to spectroscopy of solar system objects, aren't disconnected topics that happen to use the same instrument. They're fundamentally connected aspects of planetary science and astrophysics. Because if we genuinely want to understand how common Earth-like worlds might be throughout the galaxy, or how life could persist under harsh conditions very different from Earth, or what primordial planets resembled when the universe was young, we require all of it. Not exclusively the distant galaxies showing us cosmic history, not exclusively the biosignature candidates around other stars, but the complete observational picture from our immediate surroundings to the edge of what we can detect across cosmic time. Only by understanding planets in our own solar system can we properly interpret what we see around other stars. Only by observing how young galaxies evolve can we understand how conditions for planet formation changed over cosmic time. Only by detecting asteroids and comets can we understand how volatile materials like water are distributed throughout planetary systems. It all connects. By this point, having reviewed just some of Webb's discoveries across its first few years, it's unmistakable that James Webb isn't simply another space telescope, another incremental improvement over what came before. It's not a sequel to Hubble with marginally improved specifications, slightly better resolution, slightly better sensitivity. It's not a mirror suspended in space that happens to see slightly further or slightly more clearly. It's something fundamentally different that's revolutionizing multiple fields simultaneously. Something that's quietly but profoundly reshaping how we comprehend the universe and our place within it. Not through sensational headlines or theatrical announcements designed for maximum media impact, but by accumulating the kind of rigorous observational data that transforms everything gradually over time through patient systematic study. That transformation isn't consistently dramatic or immediately obvious. Most often, it's simply a shift in what questions we're even permitted to ask scientifically, what hypotheses we can actually test with real data rather than just speculating about. Before Webb began operations, we possessed educated guesses about the early universe based on extrapolating known physics backward in time. Now, we possess actual measurements of galaxies from that epoch. Before Webb, we could detect an exoplanet's existence through transit photometry and radial velocity. Now we can characterize its meteorology, its cloud patterns, its detailed atmospheric chemistry molecule by molecule. Before Webb, we assumed galaxies evolved gradually over billions of years through hierarchical assembly, Now, we've observed them form rapidly, flourish briefly, and fade into quiescence all within the universe's first billion years, forcing wholesale revision of galaxy formation theories. And that's the fundamental shift we're experiencing. Not merely growth in what we know, adding facts to our encyclopedia of cosmic knowledge, but transformation in how we conceptualize what's physically possible, what processes can occur, what timescales govern cosmic evolution. Because what this telescope has demonstrated repeatedly across diverse observations is that the universe didn't evolve slowly and predictably according to our comfortable models extrapolated from local observations. It evolved rapidly and sometimes violently, especially in its youth. Galaxies achieved massive scale faster than we believed physics permitted. Black holes didn't patiently wait their turn in the cosmic queue, growing gradually through steady accretion. Stars formed, burned through their nuclear fuel, and passed their processed elements forward in cascading generations long before we were supposed to be capable of observing any of this. And yet, there they all are, unambiguously clear, sitting in Webb's observational data, demanding explanation. The observations are real. The data is solid. The challenges to theory are unavoidable. So we're left in an unusual intellectual position, one that's simultaneously exciting and uncomfortable for theorists. A position where some of the most significant answers Webb has provided have generated even more profound questions requiring investigation. Why were so many galaxies already structurally mature, already containing substantial stellar populations, when they shouldn't have possessed sufficient time according to standard models? How did supermassive black holes manifest so early in cosmic history, achieving billions of solar masses in mere hundreds of millions of years? And what physical mechanisms enabled them to feed so voraciously, to grow so rapidly despite theoretical limits on accretion rates? What kinds of worlds exist out there orbiting distant suns that could harbour not merely water and simple cloud systems, but complex molecular signatures including organic compounds we've only ever encountered here on Earth in association with life? What fraction of exoplanets might have atmospheric chemistry that appears biological, and what fraction of those appearances are real versus mimicked by exotic abiotic chemistry? And perhaps the most honest, most humbling question of all, how much of our theoretical understanding was constructed on models that were simply too orderly, too gradual, too simplified to match the messy physical reality of how the universe actually evolved? Webb isn't here to validate what we assumed based on extrapolation and theory. It's here to challenge those assumptions, to test them rigorously, to ensure we're not merely constructing narratives that feel intuitively correct, but ones that genuinely correspond to what's actually out there in the cosmos waiting to be discovered. And we must remember, it's still remarkably early in the mission. Webb launched in late 2021, began science operations in mid-2022. We're just over 3 years into what could hopefully be a decade or more of operations. There are literally thousands of observations in the operational pipeline that haven't been publicly released yet. Data that's been collected, but awaits analysis and publication. Entire surveys that will continue running for years, systematically mapping the sky in infrared wavelengths. Legacy programs that will consume thousands of hours of telescope time. Future missions already being planned to complement Webb's results, with new instruments operating in different wavelengths, ones that will observe in ultraviolet or optical wavelengths, or achieve comparable resolution through alternative techniques like interferometry. Each will add pieces to the puzzle Webb has begun revealing. And then there are the discoveries we haven't even imagined yet. The surprise is inevitable with any sufficiently powerful new telescope. The quiet anomalies that initially seem like instrumental errors but turn out to be real phenomena. The unexpected patterns in background galaxy distributions that hint at large-scale structure we didn't anticipate, the leftover questions from redshift measurements that don't quite align perfectly with predictions, suggesting missing physics in our models, the peculiar atmospheric compositions on exoplanets that don't match any formation scenario, the gaps in stellar mass distributions that imply entire populations of objects we've overlooked, the lens transient events that might signify something more significant than we initially recognize, perhaps gravitational wave sources, perhaps something entirely new. Because the essential characteristic of a telescope like this, the lesson from every major observatory that's ever been built, is you never genuinely know what matters until you actually look at the sky with new eyes. And when you finally do look with unprecedented sensitivity, it's invariably different from expectations. Nobody anticipated in advance that Webb would discover so many galaxies that ceased star formation before they barely started, becoming quiescent in the first billion years. Nobody predicted confidently we'd obtain hints of potential biosignatures from a planet 120 light-years away this soon in the mission, in just the first few years of observations. Nobody expected to achieve such crystalline detail across such an enormous range of targets, from the furthest galaxy ever observed at cosmic dawn to the detailed cloud structures on a gas giant practically next door to us. But that's precisely what Webb is accomplishing. Not occasionally, not sporadically when conditions align perfectly, constantly across nearly every observation, revealing new phenomena and challenging assumptions. Every time it observes, it teaches us something new. Every deep field contains surprises. Every exoplanet atmosphere shows unexpected features. Every galaxy at high redshift challenges formation models. This is what revolutionary science looks like in practice. And in doing that, in making these discoveries month after month, Webb has quietly transformed astronomy from a field that necessarily relied on hopeful estimation and statistical inference to fill gaps in our knowledge to one increasingly grounded in empirical evidence, direct observation, detailed measurement, and sometimes uncomfortable clarity that contradicts comfortable assumptions built up over decades. It's not about aesthetically pleasing images, though those certainly help public engagement and inspire the next generation of scientists. It's about finally perceiving what's genuinely real out there in the cosmos, measuring it precisely, and letting reality guide our theories rather than forcing observations to fit preconceived models. And if this represents what the first 3 years look like, barely scratching the surface of Webb's capabilities and scientific potential, then the next decade isn't just exciting from a scientific perspective, it's going to fundamentally change everything we thought we understood about our universe's history, about galaxy formation, about black hole growth, about planetary atmospheres, about the prevalence of worlds that might harbour life, and ultimately about our place within cosmic history. The story is just beginning, and we're privileged to witness it unfold.